Algebra 2.1, this is Mr. Carlson, C-squared mathematics. We are going to learn higher roots. So a lot of radicals today. But before we do that, bell work, homework quiz on complex numbers, and then we're going to get to the lesson. Hopefully it's about as short as the last video. So these are two of the bell work questions I want to get to, but I have another one on the next slide that's a little bit too big to put on this. So a total of three. Let's get to it. Right here, complex numbers. Divide the following. Well, how do I do that? Well, if you remember from the last lesson, what we did was we actually multiplied by what we call the complex conjugate. What is the complex conjugate? That is the same number from the bottom, and I'm going to choose the bottom number, but instead of the bottom denominator, the whole of the denominator, and instead of a positive, I'm going to make it a negative. Why? Because what I do here is I'm going to ensure that the imaginary numbers go poofy from the denominator. I don't want any imaginary numbers in the denominator. I want them to go away. So what I'm doing here is ensuring the fact that they do go away. Why? Because in FOIL, all I need to do here is multiply the first and then the last term. The outer and the inner term, the O and the I in FOIL, when I FOIL this out, the outer and inner terms, they actually are the ones that go poofy. And those are my imaginary terms. Which means when I do it this way, in making sure there's opposite signs here, it will ensure that they go poofy. Now, I need to make sure that the opposite sign is with the imaginary number. Okay, because that's what I want to eliminate. I want to make sure that the opposite sign goes to the imaginary number. Okay? Awesome. Now what I do to the bottom, I do to the top. So that means if I multiply here, I have to multiply by the exact same thing. Now again, I want to multiply by the bottom here. I want to choose these numbers on the denominator, because if I choose the numbers in the numerator, all I'm doing is eradicating or erasing the imaginary numbers in the numerator, not the denominator. But I don't care about the numerator. I care about the denominator. So when I multiply this through, watch, this is now going to become 3 times 6 is 18. 3 times negative 4i is minus 12i. And then I'm going to take the inside. So 4 times 6 is plus 24i. And then 4 times negative 4i times negative 4i is going to be minus 16i squared. This is all over. Now watch what I do here. I'm only going to take 6 times 6, which is 36. I'm going to trust the math and just do my last term, which is 4i times negative 4i, negative 16i squared. Okay, I'm not going to do the outer and the inner terms because I already know they're going to go poofy. That's why I said 6 minus 4i on the bottom here. Of course, like I said, what I do to the bottom, I do to the top. Now, first off, never, ever, 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 never just go poofy on these negative 16i squared. If you do that, you're killing my cat. I love my cat. Don't kill my cat, okay? That is a mathematical error in algebra. You cannot do that. You need to simplify the numerator first, and then you need to simplify the denominator. So, numerator, what is that? That's just going to be plus 12i. So this is just plus 12i. And what is this right here? That's actually going to turn into plus 16 because I squared is negative 1 and then times negative 16 plus 16. So what do I have? I have 18 and then plus 12i and then plus 16. On the bottom, I do have another I squared. That becomes plus 16 as well. So it's 36 and then plus 16. Okay, so now when I start going to town on this, these actually, the 18 and the 16, that becomes 34. So this actually is going to be 34. And then this is going to be plus 12i. And then this is all over. 36 plus 16 is actually 52. And now I see that I can actually divide a lot of this by probably some number. But before I do that, I'm trying to think about the number that I can divide each of them into. That's the highest. So 2, it looks like, is probably the highest, which sucks. I know that's not the case. So here's what I'm going to do. I'm actually going to split it up first. So I'm going to split this up first, and then you can start seeing a little bit more of how you can simplify these. So 34 divided by 20, divided by 52. You can actually take each one, I think, divided by some number, divided by 2. Oh, man, I guess that's the highest, at least for here. So 34 divided by 2 is 17, and 52 divided by 2 is 26. I guess that's the highest number there. And then right here, I can take each one divided by 4, right? So that's a higher number. So that's going to be 3i, and then divided by 4 is 13. So this one was kind of complicated towards the end just because of the numbers trying to divide, simplify. But the more complicated piece is right here. Now here is just going to be subtract. So I need to make sure I have all my negatives distributed. I don't, so that means I need to change all the signs here. Okay, all my numbers are distributed. Now I can start combining. 8 plus 1 is 9, plus 5, that's going to equal 14. And then I have negative 5i, and then plus 1i, which is just going to be minus 4i. It is that simple. These questions will be on your homework quiz, so I hope they were easy for you. If not, don't take the homework quiz. Go back, review some of your homework a little bit more. I'm going to erase this, and we're going to go to our last question on the bell work. So this question is going to be over absolute value of complex numbers. So the first thing we want to do is actually plot the thing. And remember, this is the same thing as writing my real numbers, comma, my complex numbers, which is the same thing as saying my real number here is 12. My complex number here is 5. So I'm going to go up to 12 all the way over. I know I don't really have it here, and then up to 5. So it's like right here or so. So right there is going to be 12 plus 5i. Okay, so it's going to be somewhere around there. Okay, because this right here is 5. And 12 is like right here. Let's just say it that. Awesome. So now what is this formula? This formula right here for the absolute value, it's going to be a squared and then plus b squared. It is literally the Pythagorean theorem. So what you're trying to do, guys, is you're trying to find what's the distance between the origin and this point right here. And so what you do is you literally just do the Pythagorean theorem. So this is 12. So what I'm going to do is take 12. So 12 squared. And then plus, up above right here is 5. So 5 squared is 25. Okay. And so now I'm going to do 144 plus 25, which equals 116. 169, not 116. 169, which of course equals 13. So that means this value right here, this is what we found, guys. This value, that distance is actually 13, whereas this distance is 12 and this distance is 5. And so what we did was we really did a triangle here. You don't need to know that. My answer is just 13, and that's all you need to know. Okay, just follow this formula right here, and then you'll get your answer. And that's it. That's the whole for bell work. Okay, that's everything that you need to know for bell work. So I'm going to erase, get this down. Make sure you have your notes out. Make sure you're actually following along with the bell work. For your homework quiz, 25 minutes, 5 questions for complex numbers, and then we're going to begin using higher roots. So pause the video if you need to take the homework quiz. Higher roots. How do I simplify radical expressions with roots higher than 2? And how are they useful in solving complex number operations? They're going to be extremely useful. And we're going to be mainly using them next week. So this is kind of like a halvesies. You can answer the first half, but not the second half. So hopefully by the end of this lesson, you'll be able to simplify radical expressions. Expressions, not equations. That's going to be next week. Radical expressions by using what we call higher roots. So let's get into it. Ready? First thing I want to tell you, there is such a thing as a higher root, okay? There is such a thing as a higher root, and that is if I take not just 9 squared, we already know 9 squared is 81. Yes, I know that. But what if, and I also know the square root of 81 is 9. Now, I can also take 9 cubed, which is 729. And now I can take the cube roots of this. So the cube root of 729. So that is really what we're going to be doing today. We're going to be taking the cube root of stuff. Sometimes we'll take the fourth root, sometimes we'll take the fifth root. Very rarely will we. Mostly we'll be doing cube roots, okay? And we'll see that relationship there. So this is really the definition, guys. The definition is this. So you have the nth root power, whatever that is, the nth root, that could be 3, 5, 7, whatever, of a, and that will equal some number, okay? But I can reverse it and say, well, that number to that power equals a. And that's what I did here. Okay, that number to the power equals that a, that random number. And I can take this and put it as the index. So this index is what we call the number that goes attached to that little radical. Now, technically, there is a 2 here when we do square roots. We just never write it. Okay, just like we don't write 1x, or like we don't write x all over 1. If I have an x, I don't write x all over 1, right? I don't write 7 and then all over 1. Not normally, at least. Okay, and the same thing here. We understand that we don't normally write 2 here. It's just a square root. All right. So if the index is even, this is important, then a is going to be a non-negative. Okay, it has to be greater than 0. So if I have a square root, if I have a fourth root, a sixth root, an eighth root, that means my value, my number that I get out will always be positive. Always, 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 always. Always, okay? Do you get what I'm saying? If it's even, if your index is even, then you'll always get a positive answer out, which means you can never get a negative answer out. Which means if you have a negative in there and this is an even right here, guess what that means? Imaginary numbers. To give you an example, if I have this, -6, this is an imaginary number. So this actually equals I to the fourth root of 6. Okay, that's what that actually equals. Okay, in a certain sense, that's the base. We don't necessarily go through this all the time because this is actually not exactly the right answer. It's complicated. Let me just say that. So we don't actually go through that all that much, to be completely honest with you, because we don't need to. We mainly just stick with I squareds and we mainly just stick with cube roots. But this is very important, okay? Because even if I take 6 to the fourth power, even if I put that in parentheses and it's negative, it always has to come out as a positive. It always has to come out as a positive. If I take -2 to the 10th power, it always has to come out to be a positive. Okay, so that's what it's saying here. Now, if b, though, is also non-negative, and b is also non-negative, yeah, that's just kind of going after what we just said. B, this number right here, is also non-negative, which we already said. Now, if n is odd, so if your index is odd, a and b can be any real numbers. So it can be any real number at all. It doesn't need to be an imaginary number like this would be. That would be an imaginary number. If that confuses you, do not fear. I am here, which means I'm gonna try to alleviate all this in a little bit when we go through examples. So here's some common roots that we more than likely will see. Math Excel will more than likely use a lot of these roots. The cube roots are probably the most important. So the cube root of 1, of course, is 1. Cube root of 8 is 2. Cube root of 27 is 3, and so forth. Sometimes we use the fourth root here, but not likely. And then the fifth root, sometimes we use a fifth root, but again, not likely. So I would, if I were you, at least write these down so that you can at least have them. You can reference them, because in this lesson, we're going to be referencing them, at least most of them, quite a lot. So let's move on to this slide. Now, this slide is going to essentially be a review. Technically, it's a review, if I can say that. But it's just like square roots. So we did all this with square roots, hopefully, when we were in Algebra 1. And I did a little bit of it a couple days ago when we went through our videos for square roots of imaginary numbers. So essentially what it is just properties. So if I have two numbers multiplied together, underneath the radical, I can separate them, and then what I have is still the same index, n and n, whatever number that is, but I can separate. So for instance, An example of this would be as such. I can do, let's just say, an easy one, 25. I can separate this to be radical 5 times radical 5. Now notice my 2 is still here. I just don't write it. 2 is still there, and 2 is still there. Make sense? Or if I have cube root of 8, I can break this down to be the cube root of 4 times the cube root of 2. But I can break it down even further to say the cube root of 2 times the cube root of 2 times the cube root of 2, which of course equals 8, because 2 times 2 times 2 is 8. 2 to the third power is 8. So that's kind of what that one does. Now this one right here, the next one, this one is just kind of working backwards. So I don't really need to go too much in depth. It's just working backwards. If I have radical 5 times radical 5, I can combine it to be radical 5 times 5 underneath, which of course is radical 25. But of course, that just equals 5. And so that's an easy example, okay? Right here, this one down at the bottom, that just means this. So if I have radical 3 all over 4, what this equals is radical 3 all over radical 4. And then I can simplify even more because I know radical 4. So this would be radical 3 all over radical 4 is 2. Okay, so that's what that property says. This property says the exact same thing, just working backwards. If I have radical 5 all over radical 7, what I can do, if they're the same index, let's put this as 4 here, my index of 4. Since they're the same index, what I can do is the fourth root of 5 all over 7. I can combine them now into one big blob. So why is that important? Why do we care? Because I'm going to be using those properties when simplifying this stuff. I'm going to be using them. Not right now, but eventually we will. Okay, I will be utilizing these, so you need to make sure you at least have the number examples down. You don't need to know this. You can write that down if you want. I'd like you to, but if you'd rather just put them with numbers like this off to the side, my red, then that's fine. Okay, simplifying higher roots. Okay, so what is this? Now, the cool part is most of these you can actually plug into your calculator. I'm dead serious. You could technically plug them in, even Desmos. You can pretty much plug into your calculator. Not all of them, though. So if you want to ensure you get the right answer all the time, here's a lovely TI-36X Pro at a local Walmart near you, okay? Please, 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 if you have the money, if your parents have the money, it's definitely advantageous for you to get it because a lot of these you can just plug in. So for this one, I'm actually going to plug into the calculator. I'm going to show you. If I do the cube roots, so the cube root of negative 64. So you see it? Cube root of negative 64. Maybe it's kind of flipped. It's probably flipped. I don't know. We'll see. If it's flipped, I really apologize. How about if I do it that way? Can you still see it? There you go. There. So negative 64, you see it right there. Okay. If I hit equals, I get that number. So obviously negative 4. I hope you guys can see it. So that is awesome. And Math Excel is going to give you a lot of questions like this. I'm going to show you how to do most of it by hand, but I'm just telling you, this calculator is great. Okay? I like this side better. Okay, so how do I solve it by hand? Well, clearly it's 64. So what I'm going to do is I'm actually going to do this. Now, since it's negative, I'm going to do negative 8 and then times the cube root of positive 8. Now, only one of them needs a negative because if it's a negative, I can just, it doesn't matter which one I put it on. If I put a negative in both, it becomes a positive when I multiply it. That's not what I have, right? Now, so I have a negative on one of them. Now I can simplify each of these. Okay, so I can simplify this to be 4, 2, and this is 2 and 2. And so this really becomes 2. But now notice, I circled 2 here because I'm so used to square root. But notice the index. This is the important part. It's 3. So the index is 3, which means I'm going to circle 3 numbers that look alike. And they come out to be 1. So instead of a square root, so if you had a square root, right, let's just say 4, I would go 2 and 2, and I would circle the pair, and I'd be like, oh, it's therefore 2. Yes, it is, but since we did that, it was a square root. So since it's square root, we only circle two numbers. If it's a cube root, we circle not two numbers, but three numbers of the same number. So 2, 2, 2, those are three twos. So they come out to be 2. Now notice though, since there's a negative, we tag a negative on. Now you may be thinking, why is that imaginary? Because again, look at the previous slide. This is an odd index, so it can be a real number. How so? Well, think about it, guys. If I have -2 times -2 times -2, what does that equal? Does that equal a positive? So if I have a negative here, it would be imaginary? No, it actually equals a -8. These two numbers become a +4, but times another -2 gives me a -8. So you can actually have the cube root of a function and not have it at all be imaginary. Same thing with the fifth root of a function, a seventh root, a ninth root, an 11th root, a 13th root, because they're all odd numbers. So if you have an odd number, you will always have a negative or a positive pulling out. It will always be a real number. It's only when you have an even index in which you have to be careful, because you could have an imaginary number there, because you don't get negatives underneath the radical like this. Now, I still have to solve the rest. So right here, it's just +8, which just means 2. So, of course, -2. So we did get that on the calculator. I showed you we got that on the calculator, right? So the same thing is true. You can plug it in the calculator, or you can do it by hand. Now, let's do a couple of these. I'm going to do all of these. I'm going to just show you all of them right now. Let's start hashing these out. Okay, now think about this. This is even, okay? Now think about, excuse me. Okay, think about the radical here. It's an even index. Now think about this 4. It's underneath the fourth root, which means just like this, if I take this, guys, what happens? Okay, the squared goes away with the square root. So I just have -3. So the fourth goes away with the fourth root. So I just have -3. And that is really nice. Now, you could have plugged the first one on Desmos. You could have plugged this one on Desmos. I'm not going to show that to you, but you could have done that, okay? This one you could also plug into Desmos, but the problem is you'll get a decimal, because think about this. It's the cube root of 16. Now, this isn't so nice. I can't just look at my tables, my common higher roots, and actually simplify it. I need to simplify this by hand. So this is actually 4, this is 2, and this is 2, and then 2. Okay? Or sorry, this is 4. 4 times 4. Let me erase that. 4 times 2 is 8. Still even. So this is 2 and 2. Now watch what I do here. Since it's a cube root, I circle 3 of them, and then they come out. So that means this will actually be 2. Okay, it will actually come out to be 2, and then what's left over is a lonely 2. So 2, and then this is the cube root. So this is my final answer. Desmos cannot do that for you, but your lovely TI-36X Pro absolutely can. Okay, you can get this at a local Walmart near you, about $20. Now, what about this? Now, notice how it's an even number and it's a negative. So we can simplify this if we wanted to using imaginary numbers, but I'm not going to teach that to you. This is actually just not real. Okay, this is actually not a real number, and that is my final answer. It's not a real number. Instead, it will be what we call a complex number, okay? Because it's even, so it can't have a negative underneath the radical. If it's an odd, like this, it can absolutely have a negative underneath the radical. Now you may be saying, well, this was even, it had a negative underneath the radical. True, but you can simplify it further to eradicate that radical to just have the answer, and that's what we did. You can't do that here. Now, if this had a 4 right here, and this is in parentheses, yeah, absolutely. But it doesn't, so we can't, so that means it's going to be not real. Okay, now this one, pay very close attention. We're going to be doing the exact same thing, Okay, we're going to be doing the exact same thing here. You see 15 on index. You see 15 here. Now you may be thinking that, yeah, it's going to be negative, and you're right. I'm going to actually plug it into the calculator to show you. So, let me go here. Hold on, give me a second. I'm going to plug it into the TI-36X Pro. You can plug it into Desmos, but I'm not going to show you. I'd rather show you on the calculator. So this is going to be parentheses, -7, and then to the power of 15. Okay, so let me go over here. Boom. Okay, you see that? So it is -7. It's really nice. Oh, shoot. I just remembered. Okay, so that's -7. Give me a second. How much do you guys love me? Because this is awful. This is a rookie mistake for me. This is actually a positive. And the reason why it's a positive is because it can never pull out a negative. So sorry, this actually will equal a +3. The reason why it is because it's an even, and evens will always be a positive. So if you take -3 times -3 times -3 times -3 to the fourth, like four times, you will get +3. You won't get -3. So my bad, I'm sorry. But here you can take -7 times -7 times -7 times -7 all the way till 15 times, and then you'll still get -7 out. Do you guys hate me? I'm sorry. Rookie mistake. I caught it though. Okay, so all right, so now let's get to this one, and then we're going to be rolling on a lot of examples here. So this I can actually break down in a couple of different ways. I can break it down to be like this using my properties, and then all over the cube root of 27. Now notice I'm putting the negative right with the 1. It doesn't matter. But this will actually just become a straight up -1 as per my rules for higher roots. I can take -1 times -1 times -1. I still get a negative back. That's okay. All right, but down here it's not negative, so I don't have to worry about it. And then you can use your higher roots answers, whatever, cheat sheet in the last slide, and that is the cube root of 27 is of course 3. If you plug straight up that on the calculator, even on Desmos, you would still get that. Okay, so some of them like this you won't be able to plug on Desmos, but most of these you'll be able to plug on Desmos and you'll be able to get the answer. But on the TI-36X Pro, you will get this plus all the others. That's why I think I like using it. Okay, let's erase. Let's actually get to some variables. Now that's the basics of how to simplify higher roots. How do I simplify higher roots with variables in them? Okay, so this is actually hardcore Algebra 2 stuff. So let's get started. How do I actually do this? How can I simplify higher roots with variables? Well, there's an easy way, and then there's a hard way. Okay, I'm going to show you the hard way first. I'm going to show you the easy way, the shortcut. So this actually equals, ready? What is 14? Why does the 14th mean? What that means is this is the cube root of y times 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 y. Pretty sure that's 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is the hard way. What does this mean? Well, think about it, guys. What I'm saying is 3. So the index of 3, which means I need to circle 3 y's at a time. So that's one pair. So that means this becomes y times y, another pair. And then this is another kind of pair. I use pair lightly. Obviously, it's not 1 and 2. It's not a pair of 2. It's a pair of 3. And then another set. But what's left over? 2 y's are left over. So times the cube root of y squared. So what does this equal? This equals y times y times y times y is y to the 4th times the cube root of y squared. This is my final answer. That's the long way. That's a long way. How do you do it the easy way, the short way? And I'll kind of summarize everything that we did here. Easy way, ready? Easy way is this. How many times does 3 go into 14? How many times? How many times does 3 go into 14? You should say 4. That's why I have a 4 right here. Why? 3 times 4 is 12. How many are left over to get to 14? How many more do I need to get to 14? Well, 2. It's 12 to 4 is 2 units, right? 14 minus 12 is 2, right? So that means 14 minus 12 is 2. I have a squared right here. That's what's left over. So how many times does 3 go into 14? 4 times. That's my y to the 4th out in front. And then what's left over? What can't I get to? Well, that's going to be underneath the radical, and what's left over is 2 more. Okay, because 14 minus 12 is 2. That's the easy way, just thinking about it, okay? And I'll say it one more time. How many times does 3 go into 14? 4, so y to the 4th. What's left over? 2, so y squared underneath the radical. The hard way is to literally list it all out and then just, okay, that's an index of 3, so I need to actually do 3 sets, or sets of 3. So I want to do sets of 3. So that's one set of 3, that's one set of 3, that's one set of 3, that's one set of 3. There's 4 sets, so y to the 4th. How many are left over? Just 2 y's, so y to the 4th, y squared. Okay, so that is how you do that question. I'm going to erase this because I need more room. Okay, how do you do this question? This looks kind of confusing. You can't use decimals on this, by the way. You can't use decimals on that either. Okay, you can't even use a calculator on this. So how do you do this? Okay, well, first of all, I'm going to use my radical properties. Notice how this is cubed and this is cubed, which means I can actually do this. Cubed, and I can put it all underneath the radical. So this is 625, and then x to the 4th all over, and then this is just 5x. I can do that. Isn't that great? So now, what is 625? What is 625 divided by 5? Well, that's 125. And then what is x to the 4th divided by x? So this is some exponent rules here. This is to the 1 power. And so what happens is I take that 1 and minus it with the 4. So this becomes x to the 3rd. Now when I have this, okay, now I can separate this. So the cube root of 125 times the cube root of x cubed. Now, the cube root of 125 is, of course, part of your cheat sheet. It's 5. And then the cube root of x cubed, well, the cubes go poofy, right? So then I just have x. That is my final answer. Boom. Done. So that doesn't look that scary after you kind of solve it, after you kind of look at it and make sure that we know how to do it. So again, I see that they're indexes, indexes. I don't know. I can't remember. Indexes, whatever. Those two numbers are the same, 3 and 3. So now I can combine it underneath one big fat solid radical of cube root, radical of 3. So now, and then I just put them both underneath, and I combine my numbers here, and I combine my variables. And that's it. That's all. All right? Actually, yeah, let's just keep it. Now this one can get a little bit more confusing, so we'll try to go to town on this. Okay? The first thing I notice is this. I have a y in here, and then I have a cube. Okay? So automatically what's going to happen is that cube and that y is going to go poofy. So what's going to happen is that y comes out, but I still have everything else left in there. And then minus, and then this is the y times the cube root of 128x. Now, when you get to this, you have to actually start simplifying it down. So we have to simplify all this down. So this is 4, this is 2, 2, this is 2, and 2. 128, when I simplify this down, this is actually 4 and 32. 4 times 32 is 128. The 4s, when I simplify it down, of course, is 2 and 2. The 32, when simplified it down, I can do it a number of ways, but I can do 16 and 2. And then this is going to be 4 and 4. And this is going to be 2 and 2. And this is going to be 2 and 2. Now, this is a lot, okay? So what does this mean? Pay very close attention. Ready? In purple. It means this. 2 times 2 times 2 times 2 times 2 times 2 times 2 gives me 128. Try it. 2 times 2 times 2 times 2 times 2 times 2 times 2 gives you 128. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 2. So 2 to the 7th power gives you 128. Now, that's what it means. Now, since it's cube root, I'm going to circle cubes. So I'm going to circle sets of 3. So I have a set of 3 right here. And so watch. I'm going to kind of separate this. I'm going to come back to this in a little bit. I'm going to separate this, okay? Whoa, what happened there? Okay. By minus, I have a y here, times, I brought out a set of 2 right here, and then now watch, I have a 2 here, 2 here, 2 here. That's another set of 2, so times 2, and then what's left over times the cube root of 2 is left over. Now, of course, I still have an x chilling in there. That's what makes this problem so difficult right here, because I still have an x chilling underneath. Okay, still have an x. Okay, but that's it simplified out. Now let's go back here and let's kind of combine these. That's a set of 2. So I have 2y times cube root. What's left over? 2x. Okay, there's an x still chilling in there. Now, when I simplify all this together, I get 2y times the cube root of 2x minus 2 times 2 is 4. So minus 4y times the cube root of 2x. Now, when I get something like this, now pay very close attention. You start to see that the indices are the same. The indices are the same, 3 and 3. Okay, and then you also see that right here, I'll highlight this in blue, that the 2 x's are the same. So not only is the 3 the same, but the 2 x's are also the same. Okay, so now that they are the same, I can actually combine these two together. What makes it even better is that you have the y attached to it as well. So literally all of it's like one big fat variable. So now all I have to do is just take 2 minus 4, which gives me negative 2. And then the rest stay as a variable. And this is my final answer. So this one was kind of nasty. I'm not going to lie. This one was kind of a nasty question, and again, go through it again if you need to. But the first thing I do is I take out the y, bring it out front. So I take that y, bring it out front. After that, I simplify down the 16 to 128. And then I put it into a radical with the x in it. Okay? And then I simplify down a little bit more. I notice that they're the same, and then I can combine. And that's my final answer. That one was really nasty. I get that. Okay, we're going to go through this one the next. But again, if you're struggling with that one, please feel free to go back and change it. Or go back and not change it. Go back and review it again and go on Math Excel and start practicing. So notice how this is square and that's also square. We just don't write it. So that means this is underneath one big fat radical, 504, and then x cubed, and this is all over 2x to the negative 7th power. Now, just because it's the negative 7th power does not mean anything. It means I'm still going to combine them, okay? So this actually means a negative and then a negative 7. That's what that means when I combine them. So I'm going to take that out, and that's what it means. I'm going to bring it to the numerator, and I'm going to take 3 minus that negative 7, which, of course, makes it into a positive, which makes it into 3 plus 7, which gives me 10. So that is what my exponent will be. I have 504 and then x to the 3 plus 7 power, which when simplified is going to be 504 and then x to the 10th power. Okay? Now, of course, I can, sorry. I forgot to divide by the 2. Oh my gosh. See, this is what makes these hard because they're so easy to forget certain things. So I forgot to divide by the 2. Silly me. I was just thinking about the exponents here. What is 504 divided by 2? Okay, 504 divided by 2 is 252. So this is going to be 252. Okay, And then of course I can simplify this more. And so it depends on how you want to simplify it. You can do 2 and 126. That's what I do. So 2 and 126. Simplify even more to be 2 and 63. This simplifies even more to be 9 and 7, which of course the 9 simplifies down to 3. So I have a lot of stuff here. Notice it's square root, so I'm going to take the 2's together. I'm going to take the 3's together. The 3 times 2 gives me 6, so this equals just 6. Okay? And then I have a 7 left over. Okay? I have a 7 left over. So this is actually going to be times radical 7. Now, notice this. Why did I leave a blank here? I'll tell you why I leave a blank. Don't forget about the x to the 10th. Now, this is square root, so now think with me, guys. How many times does 2 go into 10? It's actually rather an even number. It goes into it 5 times, so x to the 5th. And that is my final answer. So these are hard questions. I get that. These are very hard. We kind of have to wrap our minds around it a little bit longer than we normally would in math. Okay, these are very hard questions, but this is how you would simplify it. Okay, how did I do it? Combine it underneath one big fraction, underneath square root. 504 divided by 2 is 252. And then I take that negative 7, my exponent rules, I bring it up. And so I take 3 minus the negative 7, which gives me x to the 10th, which of course is what I would have here. So x to the 3 plus 7, because the negatives make it into a positive. 3 plus 7 is 10. Break down the 252. I have 2, 126, 2, 63, 9, 7, and then I have 3 and 3. The 3 combines together because it's square root, so I can do that. I only want 2 of them for the 2's, so I can do that. 2 times 2 times 3 is 6, and then I have a radical 7 left over. That's the only one I didn't use. And then, of course, how many times is 2 going to x? Or how many times is 2 going to 10? 5, so that means I bring it out, x to the 5th. These are very tricky. I remember when I was in algebra 2. I didn't understand anything. I pretty much took the blow on these questions. I mean, really, I took the blow on these questions because when it came down to variables, I struggled. Okay, so please go back and review this video. Go back and try to go on Math Excel and try to understand how these variables interact with each other. Okay. I'm going to now move on to, and we'll review during bell work on the next video too. So I'm going to move on to just skip the variables, and then let's just get to operations and expressions. What happens when I have this? Well, I have to check to see if they're the same index. They are. So I have the index of 3. What is 4 times 10? It's just 40. Can I simplify this? Well, of course I can. So this is 8 and 5. It doesn't matter. I can do 4 and 10, but I'm just going to do 8 and 5. This is 4 and 2, and this is 2 and 2. Since it's cubed, I need to combine 3 numbers together, so a set of 3. So then this equals right here. Actually, let's put my equal sign right here. So this equals 2, and then I have a 5 left over. Don't care about the 4, don't care about the 8. I only care about that because 5 times 2 times 2 times 2 gives me 40. So I have a 5 left over, and of course, it's still underneath the cube root. That is my final answer. So that's some good practice there. If you plug that into the calculator, you would get that. If you plugged it into Desmos, you wouldn't get that. By calculator, I mean the TI-36X Pro. Awesome. What do I do here? Well, notice how this is the exact same thing as this, right? So since it's the exact same thing, you're going to treat it like a variable, okay? You're going to treat it like a variable. Since it is a variable, you're going to say 9 plus 5, which is 14, and then times the 5th root of 4. Can you do the 5th root of 4? Absolutely not. You can do the square root of 4. You cannot do the 5th root of 4. Awesome. We're going to town on these. Here, I have something a little bit different. I need to break stuff down. So this is actually a lot of breaking down. So this is actually going to be 3, and I'm going to take, let's just do 9. That looks gross. Don't ever say that just equals 9. Make sure you notice the index is 3. This is not 9. It's not square root. So this is 9 times 9. Of course, this is 3, 3. This is 3 and 3. Since it's a cube root, I need to circle 3 of these. So 2 times 3 times the cube root of 3, which reduces down to 6 times the cube root of 3. That's my first answer. Awesome. Okay, and now this, let's break it down. So it doesn't really matter how you do it. This is actually 96 and 2. 96 broken down is 48 and 2. 48 broken down is just, you can do 24 and 2. I'm actually going to do that. I'm going to keep with the 2's. And this is going to be 12 and 2, and this is going to be 6 and 2, which of course gets broken down to 3 and 2. Really nice, that one is. Yes, so since it's cube root, right, I need to circle 3 of them. So that means this is going to be plus, and then I'm going to do it underneath here. So sorry. So this is, so not 3. Oh my gosh. So this is going to be plus. Actually, you know what? Let's erase this. I want more room. I don't want to confuse you guys. So this is actually 6, and then times the cube root of 3 plus. Now I want to erase that. I don't want to confuse you. Okay, so plus, I circled 3 2's, so that means I have a 2 out here, times, and I'm going to circle another 3 2's, so then I have another 2 out here, and then times what's left over, my cube root of radical 3. So 2 times 2 is 4. So this is what I have so far. Nice and neat work. Now notice right here in red, these are the exact same thing, which means I can treat it like a variable. So now I just have 6 plus 4, which is 10, and then 10 times the cube root of radical 3. That is my final answer. If you had a TI-36X Pro, you can do it. How do you know? I'll do it right now for you. This is 2 and then times, 2 and then, wow. Oh man, I thought it would do it. Man, that sucks. It actually doesn't. I know it's kind of flipped here, but it doesn't do it for you. Oh, it's not flipped. Okay, great. It doesn't do it for you. Sad day. Oh my gosh, that sucks. I thought it would. Maybe I'm doing it wrong. I don't know. But anyways, you have to do it by hand anyways, right? So do it by hand, and then you won't have that problem. Okay, so let's continue on to more operations. Here is what we're going to be learning: rationalization. What is rationalization? It's very similar to the complex conjugate. So I don't want the radical underneath the denominator, or in the denominator underneath the numerator. I want the radical really on top. Okay, and so how do I do this? Well, I have to multiply by something that will get rid of this radical here. Now this one's actually rather odd, okay, because this is what makes it so difficult. I do have to multiply it by some sort of number that is a negative out front here, but that's the problem. That's what makes it so odd looking. And so I actually have to multiply this by something, but before I do that, I'm going to rearrange this to be -1 plus radical 5. Now, why would I do that? Because this is something similar to what we did before. If I have like 5i, I would need to multiply this by -1 minus 5i. Remember that? We did it even during the bell work, and then -1 minus 5i. Guess what we're going to be doing here? Literally the exact same thing, but just with the radical. And this is an advanced form of rationalization. I'm going to take -1 minus radical 5. -1 minus radical 5. Because this will ensure that the radical gets it's eradicated from the denominator. Okay. Fun fact, the form of a radical not being in the denominator, usually, if you remember from Algebra 1, it's actually a no-no. You're not supposed to have a radical in the denominator. And the reason why that is we don't really know. It's basically because it's hard to calculate by hand. Because back then, they didn't have calculators, right? 200, 300 years ago, they didn't have calculators. They had to do the radical by hand if they wanted a decimal. Think about that. I don't even teach you that, but if they wanted to actually calculate that radical by hand, okay, That's crazy. Okay, they would need to try to figure. They had tables and everything, the decimals and all that fun jazz. That's nuts. Like, think about it. How can you even do radical five? Like radical five is such an obscure decimal. It's so odd that like we don't even think about it, but we would have to do that by hand. And so dividing those radicals were often harder. Okay, were often more difficult to do instead of if we divided by like a whole number. So what they did back then was they tried to do this rationalization so that the radical would end up in the numerator and not the denominator, so it would be easier for them to actually calculate it. Do we need to do that anymore now? Not really, since we have calculators, right? And so it's just one of those things in math that we just kind of do because of tradition. We want the radical in the numerator and not the denominator. Aside from not church history, wow. Aside from math history, okay, which strongly actually influences the church. Maybe that's what I was thinking. The church and math history are strongly attached, okay, especially in the Renaissance. But aside from math history, let's think about this problem. I still want to distribute, so that's what I'm going to do. So let's distribute. 16 times negative 1 is negative 16. 16 times this is negative 16, and then radical 5. Okay? And then this is all over the exact same thing. Now watch, guys. Watch what happens. Just like with complex conjugates, the reason why I do this is so that I only need to multiply the first and the last terms. I already should know that the middle terms will go poofy. But just in case you don't believe me, I will show you just this once. So negative 1 times negative 1 is 1. Negative 1 times a negative radical 5 is a positive radical 5. Positive radical 5 times negative 1 is a negative radical 5. And then positive radical 5 times negative radical 5 is actually negative 5. I don't know why I put a 2 there. Maybe I was thinking of 25, but negative 5. Because again, radical 5 times radical 5 is radical 25, which reduces down to 5. So I know radical 5 times radical 5 is 5, and then of course the negative is there. Okay, now what happens to the middle terms? They go poofy, which is what I wanted, okay? And that's what is happening. This is what's happening here. So this is going to be negative 16 minus 16 and then radical 5. This is all over negative 4. I can divide, because 1 minus 5 is negative 4. I can divide each one by 4. Actually, I can divide each one by negative 4, so I'll actually do that. So negative 16 by negative 4 is actually a 4. Negative 16 by negative 4 is a positive 4, radical 5. And then negative 4 divided by negative 4 is, of course, 1, which we can do that, but we don't really need to. This is my final answer. Okay, so that is how you break it down. Not too bad. I mean, complicated, sort of, yeah, but not awful. Okay, so now let's go to my next question. I'm going to put both of them on the screen here. Let's do this one. So now what I'm going to do, since I like the radical, I usually like the radical on this side, just FYI. So I'm going to do this. I'm going to do minus radical 2. Again, very similar to the complex conjugate. That's why I taught it first, by the way. I wanted to do the complex conjugate first so that we're familiar with this kind of setup here. Okay, so now I can distribute. So this equals, this is 9, and then minus 9 radical 2. And then when I multiply this, I just want the first term and I just want the last term, because the middle terms, the outer and the inner, will go poofy, just like what they did here. Trust the math. So 1 times 1 is 1, and then radical 2 times negative radical 2 is just minus 2. This simplifies down to 9 minus 9 times radical 2 all over negative 1, which simplifies down to a negative 9 minus 9 times radical 2. And then, of course, we'll want to distribute that negative through. So this is negative 9 plus 9 radical 2. This is my final answer. Okay. The tricky part about this one is the distribution of the negative. Bringing it up top, like bringing the negative up top and not having a denominator there. That's probably the hardest part, I think, of that question. Now, this question is actually very difficult, so I'm not going to try to tell you to do it by hand. or by yourself. Now notice there's two radicals here, and they can't combine. You can't do anything right here. So what do I do? Like, do I just stare at it? Do I cry a little bit? Do I just stop the video and watch Netflix? No, you don't, okay? You don't. What you do is you follow along, okay? So what I'm going to do is still the exact same process, but I'm going to do something a tad bit differently here. I'm going to include the 6, the radical 6, but I'm not going to tag a negative to it. Because what I want to do is I want to eliminate it. I want to try to eliminate the radicals underneath in the denominator. And this is a fantastic way of eradicating the radicals in the denominator. Now, if I made them both negative, technically it would still, if I made these both negative, it would still eradicate it, but it would just be pointless. Like, it would be almost unnecessary negatives just chilling. Okay, and that's we don't want that. We don't want unnecessary negatives. So this is the easiest way, and I'll show you. I'll actually FOIL the whole thing out. But before I do that, let's do the numerator. So this is going to be 2 radical 6, and this is going to be minus 2 and then radical 6. Sorry, not radical 6, radical 2. Minus 2 times radical 2. Whoop-see. Okay, so now the bottom. Let's actually multiply this whole thing out, FOIL it out. I'm going to show you. So radical 6 times radical 6 is, wow, I keep thinking radical 36 or 36, but it's radical 36, which just equals 6. So radical 6 times radical 6 is 6. Radical 6 times a negative radical 2 is going to be a negative radical 12. Notice how the indices are the same. 2 and 2, square roots. So I can do that. Now right here, watch. Radical 2 times positive radical 6 is a positive radical 12. Boom. What is going to happen here? You already know. Okay, you already know that. All right. So radical 2 times radical 2 with a negative is, of course, negative radical 2, negative radical 4, which is just negative 2. And this goes poofy, which is exactly what we wanted. So what do we have now? So what we have is just a numerator. So I'm going to copy it down. And then I have 6 and then minus 2, which is just 4. And now this can actually simplify. Each one can be divisible by what do we call it? 2. So each one can be divisible by 2. And so I can take a 2 out here, I can take a 2 out here, and I can take a 2 out here, which just gives me 2. So this is radical 6 and then minus radical 2, which is all over 2. Perfect. Awesome. So now I'm going to erase, because that is how you rationalize higher roots. That's how you rationalize intense denominators. Okay, it's not really higher roots because they're all square roots, but it's still how you rationalize. So what did we learn today? We learned to evaluate square roots. We already know how to evaluate square roots, but basically higher roots as well. We learned how to evaluate higher roots as well. Use the product and quotient rules to simplify square roots and higher roots. Add and subtract square roots, rationalize denominators, and then we also evaluated and performed operations, with the vast majority with higher roots. Okay, so a lot of stuff's happening here. I'm going to explain it, and then we're going to close. So obviously, I want you to review your notes tonight. If you have any questions, ask. It's higher roots tonight. And then you will see, and I will explain this, you will see a complex numbers, roots, and quiz review. That thing is for extra credit, so plus 15 extra credit points. And that's intense, plus 15 extra credit points, I'm telling you. That's going to do something, okay? So I'd highly encourage you to do that, but that's the only time I'm going to remind you on the video. I'll remind you on the other, like in class, as much as possible. But this is C Squared Mathematics. I'm Mr. Carlson. Like and subscribe. I'll see you guys later.